Have you ever found yourself chatting with an AI? Maybe getting it to write a story, or answer some really complex question, or even crack a joke with surprisingly good timing.
Oh, absolutely. It's incredible how capable they've become.
It really is. But it makes you wonder, doesn't it? Are they actually thinking? I mean, do they process the world and, arrive at conclusions in a way that's anything like how we do?
That's the big question, isn't it?
Yeah.
You've got the human brain on one hand, large language models, LLMs on the other, both complex networks, both process information, both learn.
And on the surface, yeah, the results can look remarkably similar sometimes.
It really can.
Exactly. So our mission for this deep dive is to sort of pull back the curtain and really compare AI thinking and human thinking.
hmm
And we're not just scratching the surface here. We want to dig into six really fundamental areas:
Okay.
how we acquire knowledge learning, how we make sense of information processing, how we remember things, memory,
Right.
how we reach conclusions, that's reasoning, what happens when things go wrong, errors,
Errors. Yeah, that's a big one for AI.
definitely. And maybe the most crucial bit, how just existing in the physical world shapes our understanding. Embodiment.
Embodiment, yes. So learning, processing, memory, reasoning, error, and embodiment. It's quite a journey into what it even means to know something, whether you're, well, biological or artificial.
Let's jump right in. First step, how we learn.
Okay, learning. For humans, the key concept is neuroplasticity.
Right, that idea that our brains aren't fixed.
Exactly. It's the brain's amazing ability to physically reorganize its neural networks based on experience. Every time you learn something new, a skill, a fact, even a face, the connections between your neurons, the synaptic weights, they actually adjust.
It's that old saying, right? Neurons that fire together, wire together, heavy in theory.
That's the one. And what's really striking about human learning is just how efficient it is. We can often grasp a new concept from just a couple of examples.
Sometimes even just one. You hear a new word in context once, and boom, it's potentially locked in.
Precisely. We form lasting memories from surprisingly little data. We're constantly updating like a dynamic system, always integrating new information.
Which feels, fundamentally different from how LLMs learn. Their process sounds much more artificial.
It is artificial. By definition, LLMs learn mainly through a process called backpropagation. It's part of their training.
How does that work exactly?
Well, simplified. The model makes a prediction like what word comes next in a sentence. It compares its prediction to the actual correct word in the training data.
Okay.
Then it calculates the error, how far off it was, and that error signal gets sent backward through the entire network.
Backward.
Yeah, backward through all its layers, making tiny, tiny adjustments to millions, sometimes billions of connections or weights. The goal is to nudge the network's output closer to the correct answer next time.
And it has to do this. How many times?
Oh, billions, trillions of times across massive data sets. Think about that contrast. You might learn a new word after hearing it maybe twice.
Right.
An LLM needs to see that word potentially thousands, maybe hundreds of thousands of times in different contexts within its training data to reliably understand its usage.
And here's a key point, I think. Once that training is done, the AI model's parameters, its knowledge, is generally static, right? Frozen.
That's usually the case, yes.
Yeah.
It's like a finished book. It doesn't learn from a conversation with you in the way a human does. Its core knowledge base doesn't update on the fly.
So that fundamental difference really shapes everything else. Human intuition from maybe sparse real-world experience versus AI understanding from massive, massive statistical patterns in data.
Exactly. Leading to very different kinds of knowledge with different strengths and weaknesses.
Okay, so if that's learning how we get information in, what about the next step? Making sense of it all. Information processing.
Right, processing. Our brains are, well, mind-bogglingly parallel.
Yeah.
Billions of neurons, trillions of synapses, all potentially active at the same time.
It's not step by step.
Not at all. It's distributed. We have specialized areas, like the visual cortex for seeing, auditory cortex for hearing, all working together.
And here's something fascinating. We don't really process language word by word, do we?
No, not really. We process concepts, chunks of meaning. When you read a sentence, you're not just decoding symbols. You're grasping the underlying idea, linking it instantly to your existing knowledge, the context, your expectations.
Our brain is content addressable, I've heard it called. Like a concept triggers related ideas.
Precisely. A single idea can activate a whole network of related memories, concepts, even predictions about what comes next.
Okay, Contrast that with an LLM. How does it process input?
LLMs work with something called tokens. These are discrete units to be a
Hmm.
whole word, part of a word,
Lots
punctuation.
of building blocks.
Sort of. When you give an LLM input, say a sentence, it first encodes that text into numerical representations,
Yeah.
vectors. Then it passes these vectors through multiple layers. And in those layers, it calculates attention scores. This is a mechanism to figure out which tokens in the input are most relevant for understanding the current part of the text and predicting the next token.
So it's more about predicting the next logical piece in the sequence based on patterns.
Exactly. It's incredibly sophisticated pattern completion based on the statistical relationships it learned during training. It operates primarily at the level of these tokens, not at the level of, abstract ideas or understanding in the human sense.
Which helps explain why they're amazing at language tasks but can lack deeper meaning or common sense. They're manipulating the symbols of meaning very effectively.
But without necessarily grasping the underlying concepts those symbols represent.
Right, and that leads us straight into memory. Because processing information is one thing, but holding on to it, that's crucial.
Crucial, and again, very different. Humans have these multiple interacting memory systems. There's this super brief sensory memory gone in seconds.
Like the echo of a sound.
Exactly.
Yeah.
Then there's working memory, our mental scratch pad. It holds what we're actively thinking about, but its capacity is quite limited.
Right, you can only juggle so many things at once.
And then there's long-term memory. This is the vast storehouse, potentially holding information for years, decades, a lifetime.
And the really wild thing about human long-term memory is how associative it is. It's not like files in a cabinet.
Not at all. Memories are linked by meaning, by context, crucially, by emotion.
Yeah, I have this thing where a specific smell, like this one brand of glass cleaner, instantly takes me back to this tiny video studio I worked in years ago. The smell triggers the place, the feeling, everything. It's so vivid.
That's a perfect example of associative recall. The smell is a key that unlocks a whole network of related information and feeling.
So how does an LLM's memory compare to that?
Well, it's much simpler. You could say its long-term memory is basically everything it absorbed during its massive training phase, all encoded in those static weights we talked about.
Okay, so all its knowledge is baked in from the start.
Largely, yes. The AI equivalent of working memory is something called the context window.
The context window, I've heard that term. What is it?
It's essentially the sequence of tokens the model is currently looking at. That includes your prompt, the conversation history up to that point, maybe any documents you've attached.
But it's limited, right?
Critically limited.
Right.
Once that window fills up, maybe a few thousand words, maybe more, depending on the model, the information from the beginning of the conversation literally just falls out. It's completely forgotten.
Wow. So no associative links, no emotional tags. It just drops off the end.
Exactly. If your chat goes on long enough, the LLM genuinely has no memory of what you discussed earlier, outside that fixed window. It lacks those rich, interconnected, long-term structures we have.
Okay, so learning, processing, memory, all pretty different foundations. What about reasoning, getting to conclusions?
Reasoning. For humans, cognitive scientists like Daniel Kahneman talk about two systems. System one, fast, intuitive, automatic thinking, your gut feelings.
Right, happens without effort.
Then there's system two, slow, deliberate, effortful, logical reasoning. When you consciously work through a problem step by step.
And we know we're doing it. We can explain our logic, backtrack, correct ourselves. It's a conscious process.
Yes, that conscious element is key. Now, LLMs, they are primarily trained on the outputs of human system 2 thinking.
Meaning
They've learned from vast amounts of text that contains well-structured arguments, logical explanations, factual information stuff humans produced using system 2.
so they learn the patterns of logical sounding text.
Exactly. Techniques like reinforcement learning or chain of thought prompting can encourage a model to output intermediate steps that look like reasoning.
Chain of thought, right, where you ask it to think step by step.
Yeah, but here's the crucial distinction. The LLM isn't consciously performing reasoning like we do. It's generating a sequence of tokens that is statistically plausible and resembles reasoning based on the patterns it learned.
So if it gets a math problem right, it's not because it understands math.
It's more that the sequence of tokens representing the correct mathematical steps is a highly probable sequence in its training data. It's mimicking the form of reasoning, not necessarily performing the substance of it.
That explains why they sometimes fail at really simple, almost trivial logic tasks, right? I remember reading about models struggling to count the letter R in the word strawberry.
Yes, That was a classic example. A task a child could do easily, but it tripped up powerful models because it required a type of procedural understanding they didn't inherently possess just from text patterns. They don't get the concept of counting letters in the same way we do.
Okay. That difference between mimicking reasoning and actual reasoning, it seems vital. And it probably connects to the next point.
Errors.
Indeed. When LLMs make errors, the most talked about type is hallucination.
Right, where they just confidently state things that are completely wrong. Made up facts.
Exactly. Confident, plausible sounding, but factually incorrect statements. Now, we hear hallucination and we think of, seeing things that aren't there. That doesn't seem quite right for an AI. Is there a better human parallel?
There is, actually. A much better term from psychology is confabulation.
Confabulation. Okay, what's that?
Confabulation is when a person creates a false memory or explanation. But crucially, they do it unknowingly. They aren't lying deliberately. They genuinely believe the distorted or fabricated story is true.
Ah, okay. So it's like the brain filling in gaps to make a coherent narrative, even if the filled in parts aren't real.
Precisely. It can happen with memory disorders, but it also happens in everyday life to some extent.
Yeah.
Think about trying to recall all the details of a conversation from last week. Your brain naturally smooths things over, fills in plausible details. Daniel Gilbert called it the filling in trick.
The filling in trick. I like that.
So when you think about it that way, an LLM hallucination looks less like a bizarre AI-specific glitch and more like an extreme version of our own brain's tendency to prioritize coherence, sometimes over strict accuracy. It's trying to generate the most plausible continuation, even if that involves making stuff up.
That's a fascinating perspective. The next time you wonder why LLMs hallucinate, maybe think about how often you might confabulate small details throughout the day without even realizing it.
It puts it in a different light, doesn't
It
it?
really does. Okay, finally, the sixth area, embodiment. This feels like maybe the biggest gap of all.
I think it might be. It's quite profound. Simply put, humans are embodied beings. We exist in the physical world.
We have bodies, we interact with stuff.
Constantly. And our thoughts, our understanding, our common sense, they're deeply fundamentally shaped by these continuous interactions with the physical environment.
Give me an example.
Okay, think about the concept of wetness. For you, it's not just a dictionary definition. It's linked to the feeling of water on your skin, the sight of rain, the sound it makes.
Yeah, it's a whole sensory experience.
Exactly. Or gravity, intuitively, that if you let go of this pen, it will fall.
Of course.
Not because you read Newton's laws this morning, but because you live with gravity every second. Your body understands it implicitly through constant experience.
Okay, makes sense. How does that contrast with AI?
AI models, like LLMs, are fundamentally disembodied.
Yeah.
They exist as code on servers and data centers. They don't have bodies. They don't taste, smell, feel, bump into things, or experience the world directly.
So all their knowledge about the physical world is secondhand.
Entirely secondhand.
Yeah.
It's learned purely from text and data created by embodied humans. They read descriptions of wetness, descriptions of gravity, descriptions of objects falling.
But they don't have the grounding of actual physical experience.
None whatsoever. And this, we think, is a primary reason why LLMs often lack basic common sense about the physical world. Well, an LLM might know. A dropped marker usually falls because it's read that fact countless times. But it lacks the deep, intuitive understanding that comes from living in a world with gravity.
So it could potentially generate a story where someone throws a marker up and it just floats away.
It absolutely could, especially if it's been trained on a lot of science fiction or fantasy texts where the laws of physics are different, without having the anchor of real-world experience to ground its understanding. They aren't tethered to physical reality like we are.
That lack of grounding seems huge. It explains so much about the common sense gap.
It really does. It's a fundamental difference in the very nature of their knowing.
So, okay, we've gone through learning, processing, memory, reasoning, error, and embodiment. When we pull all of this together, what's the big picture, the final takeaway from this deep dive?
I think the main takeaway is that while AI models and human minds can sometimes produce outputs that look similar on the surface, an essay, an answer, a story, the underlying processes, the actual nature of their cognition, are fundamentally quite different across all these areas we discussed.
They arrive at similar-looking places via very different routes.
Exactly. Both systems learn by adjusting connections in complex networks, yes. Both process information, generalize patterns, make predictions, but how they do it is profoundly different.
Humans bring meaning, Genuine comprehension, common sense, grounded in lived, embodied experience.
While AI brings incredible speed, breadth of knowledge derived from unimaginably vast data sets, and an uncanny ability to mimic patterns in that data.
So they have complementary strengths, really.
Absolutely. Neither is inherently better overall. They're just different tools, different kinds of intelligence.
And maybe the most exciting potential comes when we combine them, when we leverage AI's strengths, its speed, its data synthesis, but guide it with human meaning, context, ethics, and that crucial common sense.
That seems to be the most promising path forward, achieving the best of both worlds by understanding and respecting the unique capabilities and limitations of each.
Understanding these deep differences really does empower us, doesn't it? Not just to use AI more effectively, but maybe also to appreciate just how complex and unique our own minds really are.
Well said. It fosters a deeper appreciation for the mystery and marvel of human cognition itself.